Parallel programming leverages multiple processors to execute tasks simultaneously, enhancing computational efficiency. OpenMP and MPI are key interfaces, with OpenMP managing shared memory and MPI handling distributed memory. Combining these, a hybrid model optimizes performance, crucial for complex computations. Understanding these interfaces is essential for effective parallel computing. Parallel programming leverages OpenMP and MPI to enhance computational efficiency. OpenMP facilitates shared memory parallelism, while MPI enables distributed memory communication. This hybrid approach optimizes resource utilization and performance, crucial for high-performance computing tasks. Understanding these interfaces is essential for developing scalable applications in modern computing environments. Hybrid applications using message passing interface and open multiprocessing are prevalent in large, high-performance computing systems. They offer reduced memory footprint by optimizing application and message passing interface library resources, such as communication buffers. Additionally, they enhance performance, particularly at high core counts, where pure message passing interface scalability becomes limited. Parallel programming models utilize threads or processes to execute tasks concurrently on different CPU cores. Processes interact by exchanging messages, facilitated by message passing interface, while threads share memory, allowing direct data access among them, managed by open multiprocessing. This dual approach enhances computational efficiency and resource utilization in high-performance computing environments. MPI processes are independent execution units with their own memory space, launched at application startup, and work over multiple nodes. OpenMP threads share memory space, created and destroyed in parallel regions, limited to a single node. Hybrid programming combines these, launching OpenMP threads within MPI processes, optimizing shared memory and message passing across nodes. Message passing interface excels in internode communication, enabling efficient reductions and complex data transfers. It requires explicit program state synchronization. Open multiprocessing, on the other hand, offers high-performance intranode threading, leveraging shared memory for concurrent operations with implicit synchronization. Together, they harness the best of both worlds for optimal parallel computing performance. Hybrid programming allows each process to execute multiple threads simultaneously, sharing MPI objects like communicators and requests. MPI defines 4 thread safety levels: single, funneled, serialized, and multiple. Multiple enables any thread to make MPI calls anytime, using MPI init thread instead of MPI init for more than one thread. Hybrid programming offers fewer message passing interface processes per core, improving load balance and reducing communication bottlenecks. It decreases memory usage with replicated data and allows for dedicated threads, like communication or parallel input-output. However, it introduces overhead from thread management and complicates code readability. Thread support in message passing interface and libraries is crucial. Consider a weather simulation model using hybrid programming. Message passing interface handles domain decomposition across nodes, while open multiprocessing manages loop-level parallelism within each node. This approach optimizes resource utilization, reduces communication overhead, and enhances scalability. By leveraging both message passing interface and open multiprocessing, the model efficiently processes large datasets, demonstrating the practical benefits of hybrid programming in complex computational tasks. Hybrid programming combines different programming paradigms to optimize performance. It leverages the strengths of each paradigm, such as parallel and serial processing, to solve complex problems efficiently. This approach is particularly useful in computational tasks, where it can significantly reduce execution time and resource usage. The serial code for computing P uses the rectangle method to numerically evaluate an integral. This approach involves dividing the area under a curve into rectangles, summing their areas to approximate the integral. The precision of P depends on the number of rectangles used, with more rectangles yielding a more accurate result. Utilizing OpenMP, we enhance the computation of P by parallelizing the rectangle method. This approach divides the integral's range into smaller segments, allowing multiple threads to process simultaneously. The result is a significant reduction in computation time, demonstrating the efficiency of parallel processing in numerical evaluations. Using MPI, we distribute the computation of P across multiple processes. Each process calculates a portion of the integral using the rectangle method, then aggregates results to obtain the final value of P. This parallel approach enhances efficiency and scalability, crucial for handling large-scale computations. The MPI+OpenMP code efficiently computes P by numerically evaluating an integral using the rectangle method. This hybrid approach leverages parallel processing, combining message passing interface for distributed memory and open multiprocessing for shared memory, optimizing computational resources and enhancing performance in calculating the integral's value. The deterministic Boltzmann solver addresses two-body elastic interactions in a spatially homogeneous and isotropic particle distribution. The scattering amplitude can depend on momentum, simplifying the collision integral to a four-dimensional integral due to momentum conservation and isotropy. This approach efficiently models particle dynamics in complex systems. A significant portion of computational time is consumed in the first loop of the sequential version of the hybrid deterministic Boltzmann solver. With a reasonable grid size, each time step takes about 30 minutes. Considering a typical evolution of 2,000 time steps, this results in a total computation time of approximately 1,000 hours, or 42 days. Define the number of threads, NT, within the function scope for optimal performance. Ensure NT divides N for efficient thread utilization. This approach enhances the performance of the hybrid deterministic Boltzmann solver using OpenMP, allowing for better parallel processing and resource management. The hybrid deterministic Boltzmann solver leverages message passing interface and open multiprocessing for parallel processing. Message passing interface distributes tasks across nodes, while open multiprocessing manages threads within each node. This combination enhances computational efficiency, allowing significant reductions in processing time. The integration of these technologies is crucial for handling large-scale simulations effectively. The hybrid deterministic Boltzmann solver demonstrates significant performance improvements. Sequential execution takes 1830 seconds per time step, while OpenMP reduces this to 154 seconds, achieving a 12x speedup. Combining MPI and OpenMP further accelerates the process to just 6 seconds per time step, a 306x speedup. Coding time is minimal, with OpenMP requiring 1 additional line and MPI 10 lines. The hybrid approach using MPI and OpenMP significantly optimizes computation time, reducing it from 1,000 hours to just over 3 hours. This efficiency is achieved with minimal coding effort, adding only 11 lines to the original 600. Such advancements highlight the power of parallel computing in solving complex problems efficiently.